Hello and welcome to today's lecture on introducing thermal chemistry. In today's topic, we'll be talking about energy, different forms of energy, and calorimetry. Especially we'll be focusing on enthalpy as well in this lecture. Let's go ahead and get started. So today we'll be talking about thermochemistry, which deals with a branch of chemistry that involves the heat associated with chemical and physical changes. And again, thermodynamics is the study of energy transformations. So that's what we'll be discussing in this chapter. So as we should have learned in earlier chapters, there are two main forms of energy. Those are potential energy and kinetic energy. Potential energy, as you know, is due to an object's position or composition. So an example of potential energy could be, for example, a skier or a person at the top of a mountain. So a person at the top of a mountain has a lot of potential energy. Because it's high up, it has potential energy. Another type of potential energy is due to based on composition. So we could say, for example, a filled propane tank has potential energy because the propane has energy stored in its bonds. So due to its composition, it has potential energy. So that's what we mean by position and composition. Position means the higher up an object is, the more potential energy it has. Or due to its composition, which means its chemical bonds. So for example, propane, there's energy stored in the bonds. When you fill your gasoline tank, there's energy stored in the bonds of that gasoline. So that's actually increasing the potential energy. Now, kinetic energy is energy due to an object in motion. So for example, when you fill your gas tank, you're adding potential energy. But when your car starts moving, it's converting that potential energy into kinetic energy. And so the kinetic energy is being produced from the potential energy. Your car is moving. Since it has motion, it has kinetic energy. And this transferring of potential to kinetic energy appears as work or heat. So work is some form of action. So you're doing something, you're doing work. Heat is thermal energy. So it's being released. So whenever you transfer energy, you have work, some type of action, and you have heat, which is thermal energy. And for a car, for example, while the car is doing work, it also produces heat. And that's why on a car you have to have a radiator if it's an internal combustion car, because it needs to cool the engine, because as the engine is doing work by converting that potential energy, which is gasoline, into kinetic energy, making your car move, it's doing work, but it's also producing a lot of heat, which causes the engine to get hot, and that's why you have a radiator system that cools the engine. So work and heat typically go hand in hand unless you have a 100% system that only does, system that only does 100% work, or work only system. But most types of transfers of energy from potential to kinetic involve work and heat. And so when we're measuring these energy changes in thermochemistry, it's very important to identify the system and the surroundings. Because what you define as a system and surroundings will determine whether work is being done on the system, for example, or on the surroundings, or heat is being absorbed into the system or released to the surroundings. And so that's up to the observer what they classify as the system and surroundings. So over here to the right, we have this little picture over here of a beaker with ice and a thermometer, and we have it on a heating source. And so this here See if I can draw it right. Nope, that doesn't work. So this here we're going to classify as the system. So this beaker of ice is our system. So everything else outside of this red circle is the surroundings. So what's happening in this example is heat is leaving the surroundings and going into the system. So the system is absorbing heat because it's going from the surroundings into the system. So here the system would be a positive heat. It's absorbing heat. So again, you have to determine what the system and surroundings are when doing your energy change. So in this case, the system is our beaker. The surroundings are our Bunsen burner and everything else. So the system is absorbing heat in it. So as we mentioned, there are forms of energy transfer, and the total sum of the kinetic and potential energies is referred to as internal energy, which is here is given the symbol E. Now in some books, especially physics books, sometimes they use the symbol U for internal energy, but in this book we use E for internal energy, and it's the sum of the potential and kinetic energies of a system. And so since we're only interested in the sum of the potential and kinetic energies of the system, we're only interested in the final and initial states. So what's the final internal energy and what's the initial internal energy? And since we're only interested in the final and initial states, we look at what's called delta E. So anytime you see a delta sign in front of a symbol, we're only interested in the final and initial states. So for chemical reactions, the final states is the product. The initial state is the reactants. So we take the difference between those two, we get the internal energy. And so we talked about the forms of energy. We said heat, which is thermal energy, is given the symbol Q. And we can't measure heat directly, but we measure it by measuring the temperature change. So heat cannot be measured directly. It can only be measured indirectly by measuring the temperature change of the system and surroundings. Now, the other form of energy transfer is work, and we'll classify this as all other forms of energy transfer when an object is moved by a force. So these are the two things that make up the transfer of energy from potential to kinetic energy. And so if we want to find delta E, we just take the Q and W, the heat and work of a system, and add them together. And if delta E is positive, energy is going into the system. If it's negative, it's leaving the system. And so again, the way we find delta E is we take the heat of the system and the work of the system and add them together. So for example here, if we look at this pot of water, and let's define the pot of water as the system. So the pot of water is the system, and the heat is going from the surroundings to the system. So here Q would be positive because the system is absorbing heat. Now if it only absorbed heat and no work was done, then delta E would be positive. Energy is transferred from the surroundings to the system. So that brings us, when we talk about work and energy, we've got to talk about the first law of thermodynamics. which is the law of conservation of energy. And so, as we stated, we can convert energy from one form to another. So we can convert potential energy to kinetic energy, but energy cannot be created or destroyed. So the total energy is constant. So the delta E of the universe is always going to be 0. That tells us the total energy of the constant is constant for a universe. So the universe is made up of the system and the surroundings. So again, delta E, internal energy, has to remain constant. That means you can convert energy from potential to kinetic energy, but you can't add extra energy. So whatever the total amount of potential energy you have, that's the amount that can get converted into kinetic energy. You can't make more energy, or you can't use less energy. So for example, we have this nice juicy burger, which is a potential energy food source. So in the food, there's energy stored in the bonds. So you eat the burger and you go to the gym, maybe you do some exercise, maybe approximately 45% of the energy you use when you're exercising is converted into physical work. So where does the other 55% go? It's in the form of lost as heat. So that's why when you're exercising, you're getting hot, because you're doing work and also producing heat as you convert that potential energy into kinetic energy and heat loss. So that's why you get hot when you work. Next, we have gasoline, which is for the internal combustion energy, a potential energy source of food for the car. And so when you put gas in your car, you're increasing its potential energy, but then when you start driving the car, when it starts moving, about 15 to 25% on average is used as work. The other majority is lost as heat. And again, that's why your car gets hot, because you're also, while you're doing work, you're producing a lot of heat. That's why it needs to be cool. Again, this is for the internal combustion engine. So there are some different units of energy that we use in chemistry. So one of the most common units we use is the joule, and it's the SI unit of energy. And the joule is derived from the force times the distance. If we're calculating work in joules, work is force times distance, and force is mass times acceleration. And there's a typo in this. There shouldn't be a kilogram squared in this. It should only be kilogram, because you can't square mass. At least. And so work, which is a form of energy transfer, when we want to find work, it's force times distance, and force is mass times acceleration. And so a joule is a kilogram meter per second squared. Yeah, joule is a kilogram per meter squared, meter squared second squared. So this is the most common unit used, is joules. That's what we use a lot of in chemistry. We use joules. But another unit that's a little bit older unit is the calorie. And notice the abbreviation for calorie is lowercase c-a-l. And the calorie is based on how much energy is needed to raise the temperature of 1 gram of water by 1 degree Celsius. So 1 calorie is 4.184 joules. The same as 1 kilocalorie is 4.184 kilojoules. And by the way, for joules, you can have metric prefixes. So you can have megajoules, gigajoules, kilojoules, millijoules, etc. The same for calories. You can have calories, kilocalories, millicalories, etc. Now on the back of a food label, what you're actually seeing is nutritional calories, which is a capital C, then AL. And a nutritional calorie is equal to 1 kilocalorie. And so in chemistry, joule is the most common unit. Calorie is used somewhat, not as much as joules. And then just to show you another type of energy unit that you may see when you buy, for example, an air conditioner or a heater, is called British thermal units, or BTUs. And the BTU is very similar to a calorie, except it's in the standard measurement system. So we need how much energy needed to raise 1 pound of water by 1 degree Fahrenheit. And so 1 BTU equals 1055 joules. So from this, the most important conversion factor to remember is that 1 calorie is 4.184 joules. So here we're looking at some examples involving heat and work. And again, these are very simple questions, but the most challenging part is to get the correct sign on the heat and work. So here we have a system releases 255 calories of heat to the surroundings and delivers 428 calories of work. And we'll assume, since it doesn't specify, it delivers 428 calories of work to the system. So here we want to determine what's the change in internal energy in calories when the system releases 255 calories of heat to the surroundings and delivers. Actually, no, it should be a little ambiguous. So delivers 428 calories of work. Should have wrote a better question. We'll say to the surroundings. And so heat, to give you some background, Q is positive. Heat is absorbed by a system. So when your Q is positive, heat is absorbed by the system. When Q is negative, heat is released by the system. Now for work, let's go down here. For work, we're only going to be looking at what's called pressure volume work. And there are many types of work, by the way, but we're only going to be looking at pressure volume work. And so the equation for pressure volume work is P times delta V. So you look at the change in volume, will tell you what type of work it's going to be. Remember, delta V is V final minus V final minus V initial. So whether the system is expanding or contracting will tell us the sign of work. So again, work is, it's negative P delta V. And P is an external pressure. So some external pressure is exhibited, and you have a change in volume. So this is pressure, volume, work. And so the sign of work is important. So if work is negative, then this means that delta V is positive, which means the system expanded. Work is done on the surroundings. So if work is negative, delta V has to be positive, means the system expanded, work is done on the surroundings. When work is positive, that means delta V is negative. The system contracted. Work is done on the system. Or you could say by surroundings. Work is done on the system or by the surroundings. So again, for work, we're only going to be talking about pressure, volume, work, or the equation is work equals negative P times delta V. And delta V is V final minus V initial. So when work is negative, delta V is positive, we say the system expanded, and work is done on the surroundings. When work is positive, means delta V has to be negative, and the system contracted, work is done on the system. Or you could say work is done by the surroundings. And an example of this, for example, water freezing is negative work because as water freezes into ice, volume increases. So while you're freezing water, work is being done on the surroundings because as the water freezes, the ice expands and you increase its volume. So now knowing these two things, we can calculate the Q. So in number one again, system releases 255 calories of heat. So in number one, Q is going to be a negative 255 calories, and delivers 428 calories of work to the surroundings. So here, work is going to be a positive 428 calories. So now to find Q, we just add those two together, and we get Q equals negative 255 plus 428. Get 173 calories. So that's the, delta E of the system. So energy is going into the system. Excuse me, did I do that? Sorry, I did that incorrect. Work is actually negative because work is being done on the surroundings. I just said down here. Oh, yes, negative. Work is negative. So this would be, for some reason it didn't make sense. So negative 255, negative 683 calories. So again, heat is released, it's negative. Work is done on the surroundings, work is negative. So the change in energy is negative. That means energy is leaving the system. So now here in the number 2, we have a system receives 425 joules of heat. So receives 425 joules of heat and delivers 425 joules of work to its surroundings. What's the change in internal energy? So here Q is positive because the system receives 425 joules of heat, and work is negative because it delivers 425 joules of work to the surroundings. So delta E would be 425 minus 425. So it'd be 0 kilojoules have been transferred. So I'll give you a little moment to kind of look over all of this, and then we'll continue. Now, when we're talking about thermochemistry, we want to introduce a particular type of function called a state function. And so a state function is a property that changes independently from the pathway. So it doesn't matter what path you take, it just matters on the initial and final states. And that's what we mean by a state function. So for example, if we're traveling from San Antonio to Austin, the distance traveled could depend on the path. Maybe you take I-35 straight up, or you take 281 and some back roads. But the distance traveled, again, depends on the path taken. But the change in elevation only depends on the initial state, which is San Antonio, and the final state, which is Austin. So it would be a state function because the elevation is not going to be dependent on the path. And so again, state functions only concerned about initial and final states. And the way you know something is a state function is there's a delta sign in front of the variable. So we have delta V, delta P, delta E, there's delta T. There's lots of state functions that we use. Now, opposite of a state function are path functions. And so path functions depend on the path taken. And there are only 2 path functions we're going to talk about in this chapter: heat and work. Every other function we're going to talk about in this chapter is going to be a state function. So again, heat and work are the only 2 path functions discussed in this chapter. And so heat depends on the path taken. You can have heat at constant pressure, heat at constant volume. These are all different paths taken, and we'll actually talk about those in a little bit. You can have work at constant pressure, which is the work I just mentioned on the last slide, or you can have work at constant volume. So regardless, it depends on the path. So different paths give you different values for heat and work. So over here on the right-hand side, we have the path for the formation of NaCl. And you see that different paths have different steps for heat. But the overall, the delta H is the same whether you take one path or the other. So delta H is a state function. That's why it doesn't depend on the path taken. So again, delta sign means it's a state function. Other than that, heat and work are path functions. You will never see a delta Q or delta W. So one type of state function we're going to talk about is the energy change of a chemical change at constant pressure, and that's called enthalpy. And so that's measuring the energy change. It should be energy, not chemical change. Sorry about that, another typo. And so for chemical reactions, we usually measure the enthalpy change at constant pressure. And this is referred to as H, enthalpy. And in chemistry or in chemical changes, there are two types of important works. There's electrical work, which is done by moving charged particles, aka when you make a battery or a redox reaction. And then there's pressure volume work, which we just mentioned earlier. And this is mechanical work that's done when the volume of the system changes. We discussed that early on in the presence of external pressure. Now, pressure volume work only occurs if gases are present. And so in chemistry, we look at enthalpy, and enthalpy is equal to the internal energy plus the work. And now we rewrite that, we get delta H equals delta E plus P delta V. Oops. Yeah. Let's scratch that and do the derivation of this so we don't have to worry about that. And so enthalpy, the change in enthalpy, is equal to the change in delta E plus P delta V. Now with chemical reactions, as we'll see, very few actually, my computer just crashed. Oop. Technical difficulty there. Alrighty, now we're back on track. So very few chemical reactions involve work. And I'm having some technical difficulties. Stop share. All right, we're back on track. Just a little technical difficulty. Now we're back. Sorry about that. Just a little technical difficulty there. So back to what I was saying. So most chemical reactions involve very little. Still technical difficulties. Not annotating now. So we seem to be having some technical difficulties, so we'll stop this part of the lecture here, and I'll continue with the second part here in a moment. All right, thank you.